Hi everyone. Let me know if you can hear me. I my software updated here and my audio levels are totally off. But from what I'm seeing at my end, you should be hearing me fine without any like extra popping or anything like that. So I'll start, and if you're having difficulties hearing me or if the sound levels are too high, just let me know, and I'll turn them down or adjust them. Um, Actually, the changes to the software are good. I didn't realize it until after I'd started, and all my audio levels were off. But okay, so anyhow, uh, 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 this week and last week we kind of changed the format a little bit because solving Newton's laws is a little bit more demanding. There's a bit of a learning curve, and so I thought it'd probably be best that you go through all of Newton's laws first, and then see some of the examples that I did in the pre-recorded lectures before I gave you, the assignment, and this week added, extra live stream so that we could practice these problems together. So what we're going to do today is we're going to get to two problems. Actually, I didn't for my last class. I didn't quite get through the second problem, but that's okay. And this should get you quite a ways through the assignment. And you should try that. Do the assignment as soon as possible because it is extra long, and you don't want to wait till the last minute. You won't be able to you might not be able to finish it, and then you can't get a hold of me. So try to do that as soon as possible. But this should definitely get you quite a ways through there. On Friday, I'll do a third question, which is more complicated, and it's like the later problems in the assignment. So, well, let's just start here. So my first problem is a single box, but on an inclined plane. I'm not going to do a box on a flat surface because that's kind of trivial. But this is a box on a plane which is inclined. So a 10-kilogram box is on a plane which is inclined at 45 degrees, and there's a coefficient of kinetic friction. Kinetic means that it's actually going to be moving. Okay, so there's a coefficient of kinetic friction, 0.35, and I asked two questions: what's the net force, and what's the acceleration? Okay, so just like your kinematics problems, with these dynamics problems, you start off by drawing a diagram. And the first diagram you want to draw is just exactly what you would see if you walked into a lab. And in fact, you're going to be doing a lab like this. You're going to have an inclined plane, and you're going to put a block on it and let the block slide downhill. And you'll actually get static friction and kinetic and static friction out of it. Okay, so let me switch to my other whiteboard here, like that, and let me start drawing. So we have a plane, so it's inclined at 45 degrees like this. All right, so that angle in there is 45 degrees, and there's a box on it like this. All right, and there we go. Okay, and that's what you would physically see. All right, you see here in the chat, three people are in the chat. All right, well, let me continue. Um, uh, so there's a box like that, and once you've got the actual physical drawing, the next thing is that you want to draw the forces that are acting on this box. And let's keep in mind why we want to do that. It's to get the F net. Okay, so all of this is to get F net because that comes into Newton's second law, which says that F net is equal to ma. Okay, and to get F net, it's actually a vector. And so we have to do a vector sum of all the forces on this box. And to do that vector sum, you have to resolve them into their components. And so it's best to start off by drawing these vectors and decomposing them into x and y components right off the right at the very beginning. So I like to start with gravity, okay? And to draw the gravitational force on this box, I'm going to put a dot in the middle. Now gravity technically acts everywhere on the box, okay? So we'll talk about that later. We'll have a more sophisticated idea of where gravity acts when we do rotational motion, which is the last topic in the course. But for now, we can, in these problems, approximate gravity as just acting right at the very center of the box, okay? And technically speaking, gravity acts straight down like that, okay? So that's how you would draw your gravitational force. But because we're going to be doing this vector sum that I mentioned, it's probably best to start by not drawing this vector, but drawing its components, and drawing the components which are perpendicular to the box, and drawing the components which are parallel to the box, okay? So I'm going to remove this vector right away, and I'm going to replace it with its two component vectors, One vector is the one perpendicular to the box, and another one is parallel to the box. If you add those two vectors together, they should give you exactly this vector which I drew just a minute ago, okay? But we're going to break them up into two pieces, because what we want to do is we want to get, this kind of characteristic cross where you have only perpendicular components adding to other perpendicular components and parallel components adding to parallel components, okay? And to calculate the perpendicular component, that turns out to be mg cosine theta, like that, okay? Now, I showed you why it's the cosine in the pre-recorded lecture. I'm not going to go over that again, okay? But it turns out that, there's some geometry here, and this one, the perpendicular component, turns out to be mg cosine theta, all right? And the other one is mg sine theta, all right? Now, rather than going through that geometry over and over and over again in your head, like rethinking it each time, it's probably best just to memorize that the perpendicular component is cosine, and then of course the other one has to be the sine. Okay, so the parallel component is the sine. All right, so I'll work out those values on the other whiteboard. It's kind of hard to write here, but there we go. That's gravity, and that's the first force that I usually like to look at when I do these problems. Okay, and the next force is the normal force. And the normal force, whenever you have two surfaces that are touching, like here you can see here the red that I'm drawing in there, that's the interface, the touching between the box and the surface of the plane. Okay, whenever there are two surfaces touching, there's a touching force, and that force acts perpendicular to the surface, so it's called a normal force. And so that normal force, it's perpendicular to those two touching surfaces. There it is. And we will call that Fn, like that. And then you ask, are there any other forces? And yes, there is. There's frictional force. And the way friction works is it always acts opposite the direction of the velocity. So if the velocity is downhill, like this box is slipping downhill, well, then there's going to be a frictional force. I'll do it in green, which is uphill like that. Okay. And this is actually kinetic friction, which we've been calling FF, like that. Okay. So there we go. There's the force of kinetic friction, uphill like that. And you ask, are there any other forces? Well, not really. The only other force, and it's not in this problem, but another force is like a tension if there were a string, but there's no string attaching this to anything else. And so that's it. Those are all the forces that are acting on this, okay? And you can see the two blue forces are the gravitational force, and I've broken them up into their components. And now you can see why. We get this kind of characteristic cross here, where you have the forces which are acting perpendicular to the plane, and they combine with one another, and then they're the forces that are acting parallel to the plane, and they combine with one another. Okay, so like this force here, the normal force, it will compete with the gravitational force, irrespective of the other two, because they're perpendicular. So whatever the frictional force is, or whatever the parallel gravitational force is, that doesn't matter. Those two forces are going to compete with one another, and so when we go to calculate F net, we compare those two, okay? And similarly, this force downhill like that, parallel downhill, and this frictional force uphill, they also compete with one another to give you a total force downhill. All right, and so that's why we broke them up. We broke up gravity this way. If we hadn't, then like it would have been part of gravity competing with the normal force and part of gravity competing with the frictional force. So you really have to break it up into its two component pieces. All right. So let's see here, 3 people watching, and I don't see any questions. So let me switch right now to my other screen so that I can do some calculations. And so we've got 4 components here. We've got the gravity parallel, gravity perpendicular, the normal force, and the frictional force. And let's work them out. Okay. So over here, actually, let me cut and paste this, because this way I don't waste your time with just a lot of typing. All right, so there's 2 parts to the gravitational force. There's the gravitational, can you see that? Not quite. Let me scroll down a bit. Okay, so there's the gravitational force parallel, okay, and that was, you saw a minute ago, was mg sine theta. All right, and in this problem, m is 10 kilograms. G, so there's 10. G is technically 9.8, but you know that we're rounding off to 10 to make our life easier. And then it's sine of theta, and theta, the angle, is 45 degrees. So sine of 45 degrees. And if you work that out through your calculator, that's going to give you 70.7 newtons, and it's downhill. Okay, downhill. Now, if you do the perpendicular component of the gravitational force, the equation there is mg cosine theta. Okay, and m is 10. G is 10 as well, and cosine of 45 degrees. It turns out that cosine of 45 degrees is exactly equal to sine of 45 degrees, like 0.707 and then some extra decibels after that. But cosine of 45 degrees, 0.707 multiplied by 100, and you get 70.7. So it just turns out, because it's 45 degrees, that the parallel and the perpendicular component are equal here. They're not in general, but you should know some of these special angles, like the sine of 30 degrees is a half, the cosine of 60 degrees is a half, and the sine and the cosine of 45 degrees are equal to one another, and they're like 0.707. Okay, so that tells us that takes care of the gravitational force. Next, let's look at the normal force. There's two more forces. There's the normal force, which I'll call Fn, and the frictional force, Ff. And you say, what are these equal to? All right. And let's go back to the diagram like this. Oops. Let's go back to the diagram here like that. And let's take a look. All right. So unlike kinematics, where it's mostly plugging into equations, here a lot of this is conceptual, which is what makes these problems a bit difficult. All right, so we now know that this is 70. Oh, let me do it in blue here like that. We know that this is 70.7 newtons. Okay, and we know this one is 70.7. Okay, and that, of course, we found with these equations. But to find Fn, there isn't really an equation. I mean, I guess you could say it's Newton's second law. But what you have to realize is that, as I said a minute ago, that is competing with the 70.7 newtons. Okay? So if it's competing like that, you ask yourself, well, which one's winning? Well, if the normal force is winning, then what would happen is that what that would mean is that the perpendicular component of the force is greater away from the plane, above, pulling up off of the plane, than into the plane. And what would happen is the entire box would actually lift off the plane. Okay, so you can't have that Fn is bigger than that 70.7, otherwise the box would actually lift off of the plane. Okay, well, what if Fn is smaller? In other words, the 70.7 is bigger. Well, then this box would be accelerating into the plane. It'd be like digging into it as it goes downhill, and that's not happening. The box is neither lifting off of the plane nor is it digging into the plane. And so these two forces must exactly cancel against one another. They're like playing a game of tug of war, and they're pulling against one another. They have to exactly cancel, otherwise whichever one wins, that's the direction in which it would accelerate, and it's not accelerating off of the plane or into the plane. And so you can conclude that the normal force must be also 70.7, and there you go. Okay, so not really an equation there. All it was just reasoning, and you're really reasoning using, I guess, Newton's first law, which says that if there's no there's no acceleration, there's no net force. Now, it's technically speaking no net force in the perpendicular direction, like this, up and down out of the plane. Okay, so it's not parallel. Okay, because those two are actually independent of one another, which is why we resolved everything into this characteristic x. Okay, so back over here in our other screen here, I can say Fn is equal to 70.7 newtons. And again, you say, well, how did you get that? It's just through the reasoning that I used. All right. And then finally, there's the force of friction. And you say, well, how do you get the force of friction? So kinetic friction is different than static friction, which is why in part A here I did a kinetic friction, and I'm going to do a static right after it, because I want to show you how kinetic and static are really quite different than one another. Okay, even though they're both called friction, they actually, to solve them, you approach them in very different ways. Okay, so for kinetic friction, there's a formula, and I don't have my little mu symbol, but basically the way you get the force of kinetic friction is you take the coefficient of kinetic friction and you multiply it by Fn like that. Okay, and the coefficient of kinetic friction, I give it to you, it's 0.35 like that, and the normal force is 0.707 like that. And that turns out to be equal to, let me get that answer for you, 24.7 newtons, and it's actually uphill, okay, which you can see from the diagram. All right, so it turns out to be 27.4. Now, how do you understand this formula? Like, if you want an intuition into this formula, how do you understand it? So friction, it depends on two surfaces touching, and whenever there are two surfaces touching, there's a normal force. And what happens is that the harder the two surfaces are pushing up against one another, in other words, the bigger the normal force, the more they're sticking together. And the more they're sticking together, the more friction there is. Okay? So in other words, the harder they press against one another, the more friction there is. And the coefficient of friction is kind of like the percentage. Okay? So like 0.35, that just says that the frictional force is 35% of the normal force. That's the way to think about this. Okay? And so now we have all four components. Let's switch back to our diagram so we can see them all together. Okay, and so over here, let me do this in green. Now I know that this is equal to 24.7 newtons, like that. Okay, and you know, you work this way where like you do a little bit of calculation and go back to the diagram and write in the numbers, and then once you have all the components, you can now work out what this F net is. Okay, and again, there are two components to F net because it's a vector. All right, so the perpendicular component, that's easy because we already reasoned that one out. The two have to cancel one another, and so there's no perpendicular component to F net. The perpendicular component to F net is 0 because the box isn't accelerating into the plane or perpendicular to the plane in any way. Okay, it's the other one, it's the parallel, which gives rise to an F net. Okay, and so what you have here is a tug of war between the parallel component of gravity downhill and the force of friction uphill. Okay, and the parallel component downhill is 70.7, so it's pulling down 70.7 newtons, but friction is pulling up 24.7, and you say, well, which one wins? Well, obviously, you know, the force of gravity wins. Okay, so that's the bigger force, and you say, but you know, it has to overcome the frictional force, so the total force downhill is going to be 70.7 minus 24, which is, I guess, 46. Okay, so let me switch back to the other screen here like that. Okay, and now we can write in on the next line, F net is equal to, you know, just from the analysis we did, downhill, there's parallel gravity downhill, and that's 70.7, minus the frictional force uphill, and that was 24.7 like that, and that works out to be 46 newtons like that. And of course, you know, one's downhill, one's uphill, but the downhill wins, and so the overall is downhill like that. Okay, so there you go. Did we answer the question? What is the net force? Yeah, we did. The net force is 46 newtons downhill. Okay. All right. So let me see if there's any questions in the chat there. Is everyone okay? I don't know. I didn't get any responses earlier about whether you can hear my audio, but I'm assuming that at this point you would have told me if you couldn't hear the audio. Okay, so let's go on to the next question, which is what's the acceleration? Well, you know, like Newton's second law is basically, you know, F net is equal to ma, like that. Okay, and so all of this work, the whole point of all of this work, and in a lot of these problems, there's a lot of work, you know, in terms of the analyzing the forces. All of that work is to get F net. Okay, because F net is what comes into the second law. Okay, so that says that. Now we don't want to solve for F net, we want to solve for A, and so let me just rearrange this equation, divide both sides by m, and so we get that F net, A is equal to F net divided by m, like that. And so that's going to be what? F net we found to be 46 newtons, and m we said was 10 kilograms, like that. And so that turns out to be 4.6 meters per second squared, like that. Okay, and the direction, Newton's second law, not only tells you how to calculate the acceleration, but also tells you that the direction of F net and the direction of the acceleration have to be the same, and so obviously the acceleration is in the same direction as F net. Okay, so that solves that answers that second question. What is the acceleration? You should always ask yourself the question: does 4.6 meters per second squared make sense? Well, it has to be bigger than 0, otherwise it's not moving. It could be moving downhill at a constant velocity, but it wouldn't be, if we start off at 0 velocity, it wouldn't be moving downhill if it had no acceleration, because it wouldn't start moving downhill. And it can't be bigger than 10, because that means that's free fall, and it's not free falling. It's falling along along this wedge here. And so, yeah, that makes sense. Okay, it's like 4.6. That makes sense. All right. So that answers our first problem. Okay, let me take a look here in the chat. All right. Well, 3 people still listening. I didn't get any answer to my "is everyone okay?" So I assume you're following along here. Okay. And that's the first one. Now that one will get you through the first few questions. I don't remember how many, but my first question in the assignment, to be honest, I don't quite remember it, because I made it up over a week ago. But I remember doing a problem of a box on a wedge, okay, like this, around an inclined plane. And so this is the first part of it. The next one we're going to do, let's move on to the second problem here. Oh, I'm sorry. We're not quite done with this one. So that was the situation with kinetic. Okay. So now we're going to do static. So I say repeat the entire problem. Okay. But this time the box doesn't accelerate. All right. And I asked to find the force of static friction. So to do that, let's go back to the diagram, because that's your first step. Draw the diagram again. Okay. So let me start over. Create a new whiteboard here like that. Did it work? Yep. Okay, and here's my wedge like this. Whoops, that's a bit too steep. All right, there's my wedge at 45 degrees. All right. And here's a box like this. All right. And we've got forces on it. We got the force of gravity, but right away I'm going to draw that force of gravity as mg cosine theta, like this, and mg sine theta. Okay. And you ask yourself, is that all the forces? Nope. There's a normal force, because as soon as you have surfaces touching, you've got a normal force. So there we go. There's my normal force. And is that it? Nope. There's a static friction force like this, and this time we'll call it Fs, because it's static friction. And now you ask yourself, is that all the forces? And yeah, that's it. Those are all the forces. Okay. Now, at this point, because it's the same problem as before, well, almost the same problem. This time the acceleration is 0. Okay. All the numbers, when we go to calculate things like mg cosine theta and mg sine theta, they're the same. Okay, so this number here, whoops, let me do that in blue. This one is going to turn out to be 70.7 newtons. Okay, and this one's going to turn out to be 70.7 newtons. All right, and now let's see if we can work out what these other two forces are. Okay, so we take a look at the normal force, and of course it's competing against this force, and you ask yourself, is this box accelerating up, like in the normal force direction? Is it accelerating into the plane? And the answer is no, just like above. And so these two forces, they have to cancel against one another, and so you can immediately conclude that this is 70.7 newtons. Okay, so far the reasoning is identical to the previous problem, but in some sense here we're starting from a different point. We're starting from the realization that since the acceleration is 0, the total net force is 0. So we're not trying to find the net force. In a sense, we're actually doing this in the opposite direction. We're starting from the point, from the conclusion that the net force must be 0, and then all of these forces must turn out to be 0. Okay, so you don't calculate Fs using some formula. You simply, just like we determined that Fn had to be 70.7 newtons, using the same logic, you say, well, Fs must equal this force here because the two have to cancel. Because if they didn't, then F net would not be zero. And if F net is not zero, then there would be an acceleration. Okay, so it's the same kind of reasoning that we used for the normal force, we use for Fs, and we realized that it must also equal 70.7 newtons, because if it didn't, then you'd have an acceleration. Okay, so let's go through that logic again. If this force here were bigger, that's the parallel force downhill, if that were bigger than the frictional force, then who would win? Well, then the gravitational force would win and it would accelerate downhill. Okay? Conversely, if the static friction uphill were bigger than the force of gravity downhill, the static friction would win and it would accelerate uphill, which it doesn't do. It doesn't do either of those things. So these two can't be different than one another. They must be equal so that they cancel to give you a zero net force. Okay, and that's why this has to be 70.7. So it turns out in this problem, because the angle is 45 degrees, it turns out in this problem that all the components are 70.7 newtons. Okay, now once you have that, we can go back to our other whiteboard here, and we can write down what we found. And let me just cut and paste that, because why not? Here's the reasoning. Okay, and the conclusion. Since A had to be zero, right? Because there's no acceleration. So since A has to be zero, F net has to be zero. So for F net in order for F net to be zero, these two, they're the same. Well, then in order for this to be zero, we concluded that the normal force was 70.7 and the force of static friction was also 70.7. Okay, and so we can answer the first question. Okay, the first question is, what is the force of static friction? And it turns out that the force of static friction is 70.7 newtons, like that. Okay, now the next question was, show that the coefficient of static friction is in fact greater than tangent of theta. Okay, now why? In the pre-recorded lectures, I actually proved that for an inclined plane, that if there's static friction, okay, the coefficient of static friction has to be bigger than the tangent of theta. And in fact, you're going to prove that in your lab, or you're going to demonstrate that experimentally in one of your labs. Okay, and so let's see that that actually turns out to be true. Okay, so the coefficient of static friction, all right, it's has to be bigger than or equal to the force of static friction, the force of static friction divided by the normal force, like that. Okay, notice that this is not an equality, it's an inequality. So that means that I can't tell you what the coefficient of static friction is going to be. I can only tell you what it can't be smaller than. It has to be bigger than this ratio here, but it can't be smaller than that ratio. If it's smaller than that ratio, then the box is going to slip and you don't have static friction. If it's bigger, then you're okay. Now, how much bigger, I can't say, okay, but it's got to be bigger. Now, what is that value? Well, it's pretty easy, because static friction was 70.7 newtons and the normal force was 70.7 newtons, like that, and that's equal to 1. Okay, and so the coefficient of static friction has to be bigger than 1, like that. All right, and so it could be 2, it could be 10, it could be 100. Okay, it could be 1.1. As long as it's bigger than 1, the box will not slip downhill. Okay, it can't be 0.9, then it would slip. It can't be 0.7 or anything like that. All right, now this number 1 here, actually, like I said, I proved that it's actually equal to 1. And so if you do the tangent of 45 degrees, like that, and you plug that into your calculator, sure enough, it turns out to be 1. Okay, so this is not new. You can certainly make use of tangent of theta for the coefficient of static friction on an inclined plane. Okay, with a single box, you can make use of that formula. But this example does illustrate that. Okay, so that completes our first example. Let's see if there's any questions in the chat. Okay, any questions? I'll type it in as well. All right. If not, there's our first problem. Okay. And again, it's very similar to the one that you have on the in the assignment. Let's do our second question here. Okay. So now we're ready for the second question. So this one is different because this is an example where we have two boxes, and the two boxes are actually connected by a string. Okay, and so we're going to find the acceleration of the entire system. So what does it say? A 13-kilogram box on a flat table with a coefficient of kinetic friction 0.25 is attached by a string to a 6-kilogram box dangling off of the end. Okay, what is the acceleration of the system? All right, so like always, we're going to start off by drawing a diagram. Switch to this. Let's create a new fresh board here, like that. Okay, and step number one in drawing the diagram is just draw what you would physically see. Okay, there's our table. There's my 13-kilogram box, like this. Here's my 6-kilogram box dangling off of the end, like that. Okay, and there's a string. Here's the string, and then there's a string this way, like that. And the string goes around a pulley. I didn't mention that in the problem, but it's implicit. Whoops, let me make that a little bit nicer. There's my pulley. Okay, like this. And there you go. Okay, that's what you would physically see. And this one up here, this is the 13-kilogram because that's the one sitting on the table. And this is the 6-kilogram off the end. All right. Okay, so there's step number one. Now, step number two was to identify all the forces. But you identify all the forces for each of the masses that are involved. And in this case, there are two masses. There's this one, and independently, there's that one right there. Okay, so there are two masses. And so we got to do the forces for each one of them. All right, let's start off with gravity because it's always good to start with gravity. Gravitational force for this one is going to equal mg, but there are two m's, so don't confuse them. Let's call this one m1g. Okay, and that's going to equal 13 multiplied by 10. I'll try to do the math right here, but it'll be a little sloppy, but I think I can do it. There you go. That'll be 130 newtons. Now we should probably finish this one off first, but it's okay. We can add gravity for this one. Let's do that just to show you that they're different. I mean, it's still the same formula, but because it's a different mass, we'll call this one m2g. This time for this one, you're not going to put in 13, you're going to put in 6. Okay, so 6 times 10, and that gives us a total of 60 newtons, like that. Okay, 60 newtons. All right. So, all right, let's go back to the first one. Okay, so we got gravity in the first one. Are there any other forces acting on the first one? Yeah. Okay, there is normal. Let's do that one next. Okay, so here's our normal force, Fn. And then you say, well, is there any other force? Is there friction? Yeah, there's friction. And now, which way is this thing going to move? Well, let me do the acceleration in red here. This thing is going to accelerate that way as this box accelerates down that way. Okay, so the 13 kilogram is going to move to the right, and the 6 kilogram is going to move down. Okay, and it's going to accelerate. So if it's accelerating to the right, it's going to have a velocity to the right, and so there's going to be a frictional force, and it's kinetic friction to the left, like that. Okay, so there we go. There's our force of kinetic friction, like that. All right. And you ask, is there any other force on this thing? Last time, those were the only forces we had, was gravity, normal, and friction. But there's another one. I'll do this one in purple because there's a string, and it's a string that's pulling this thing forward, and so there's a force like that, and we will call that the tension. Okay, Ft, like that. All right. So there turns out to be 4 forces there like that. Okay, now we've identified all of them. We'll try to put some numbers on them in a minute. We did already for gravity because the reason I did the gravity is because I wanted to show you how they were different. Okay, this is a mistake that I've seen made where students will sometimes confuse the 6 kilogram and the 13, and they'll say, "Oh, I've got a mass," and they'll just like plug it in for any old m, and then you get the wrong value. Of course, it makes sense that the gravitational force on the 13 kilogram is 130, whereas the gravitational force on the 6 kilogram is only 60 newtons. Okay, so let's see if we can identify any of the other numbers here. Let's see if we can do the normal force. So ask yourself, is this thing accelerating either up or down? And the answer is no. So that means that the normal force up must balance the gravity down, and that's 130 newtons. Okay, the reasoning is identical to before. This has to cancel that one. Otherwise, the box would either be accelerating up or accelerating down, and it can't do either of those things, or it's not doing either of those things. Okay, and now the next thing is, do we have the frictional force? And the answer is yes. And let me see if I can calculate it over here. Okay, so once you've got the normal force, the frictional force is a fraction of the normal force, and that fraction is given by mu k. Okay, and that's how you do that's how you draw the coefficient of kinetic friction. So it's mu k times Fn, like that. And mu k, what did I say it was? It was 25%. Okay, so it's 0.25, like this. Multiplied by the normal force, which is 130 newtons. Like that. And that's going to equal, what does it equal? Let me look up my answer here. It equals 32.5. So over here, this is equal to 32.5 newtons. Okay. Great, we've got 3 of them. Do we know how big the tension is? And the answer is no, we don't. Okay. Don't do something like, I don't know, like, oh, the tension has to balance against that one and those two are equal to one another. No, it isn't. Otherwise, you wouldn't have any acceleration. We simply don't know how big the tension is. And so we can't assign a number to the net force right now for box number 1. Okay, for a 13 kilogram box. Okay. All right, so we're kind of done, or we've gone as far as we can with our analysis of the 13 kilogram box. Let's turn our attention to the 6 kilogram. What forces are acting on it? Well, we already identified gravity down. Is there another one? Yeah, there's the string pulling up, and that's got a force Ft, and that's also question mark. Okay. Now there's a couple of things here. This tension and this tension are exactly equal to one another, okay? Which is why I didn't put any subscripts. I didn't say Ft1 and Ft2. Those two tensions are exactly the same. And the reason is, it's the third law. It's Newton's third law, okay? Acting along the string, all right? And you say, well, why is it the third law? Well, what does the third law say? It says if there's a force of one object on the other, then the other object pulls back on the first one with equal force, but in the opposite direction, okay? So equal force, opposite direction. So if you take a look at these, you go, okay, well, you told me that they're equal, but they're not in the opposite direction because, one's to the left and the other one's up, or so one's to the right and the other one's up. And you go, well, what's going on here? Like, is that really the third law? Yeah, it is. The thing is we're being a little bit sloppy. To do the third law properly, you have to take into consideration the pulley there. And if you do the pulley, you'll see that the only effect that the pulley has is to not change the magnitude of the tension. It just changes the direction. And that's why you get the same magnitude, but not opposite direction, because the pulley is changing the direction, okay? Now, I didn't do a full analysis of that in my pre-recorded lectures. I'm not going to do that now. It can be done. It's not that hard, but it really doesn't add any intuition to the problem. So yeah, these two tensions, they are equal to one another because of the third law, and the direction is modified because of the existence of the pulley. Okay, but they are the same. Okay. By the way, you might ask the question, are the accelerations the same? Okay, because I automatically assume that both blocks were going to accelerate the same, and the answer is yes. Because as long as the string doesn't stretch and doesn't like bunch up, okay, we're going to assume that it doesn't stretch, then, the 6 kilogram, if it moves down 1 centimeter, then, then the 13 kilogram has to move the same. If the 6 kilogram moves further than the 13 kilogram, well, then the string must be stretching, okay? And so since the string remains taut throughout the whole process, these two accelerations have to be the same. And that's why I didn't call one acceleration 1 and the other one acceleration 2. They're both the same accelerations, okay? But the masses were different, so I called this one M1 and I called that one M2, okay? So that just to give you the logic of how I worked that one out. Okay, so now that we've done this analysis, we've got the forces, not completely, we don't have FT, but we've gone as far as we can. Let's switch back to our other screen here, like that. And let me show you what we have for the 13 kilogram box here. Where's mine? Okay, here it is. We called it M1 like that. We have the following. We have that its weight, its mass, M1G like that, was equal to 130 newtons. Hold on here, can you see that? Yep, okay, that's good. Okay, 130 newtons, so there's the weight. Then there was the normal force, and the normal force turned out to be 130 newtons, like that, because the two had to cancel against one another. There was also the frictional force, which we worked out to be 0.25 times 130, okay? And there was the tension, which is just unknown. We simply do not know how big the tension is, okay? And so at this point, you could say, well, what's F net? And you might say, well, I can't calculate F net because I don't know one of them, but you kind of can. You can at least, push F net as far as you can determine it. So let's go back to the diagram for a second to see how we would reason out F net, okay? And so these two forces here, the normal and gravity straight down, they cancel, okay? So they're not contributing to F net at all. You can just strike them out like that, okay? It's these two that are competing, all right? And which one has to win? Well, the one that has to win is FT, because if F were bigger, then it would be accelerating that way, right? If the force of friction were bigger to the left than the tension to the right, the force of friction would win and it would accelerate to the left. But it isn't. It's accelerating to the right here like that. And so the tension has to beat the force of friction. And so over here we could write, okay, which one's winning? The force of tension is winning. Tension is winning over the force of friction, like that. And we don't have a number for the tension, but we do have a number for friction, 32.5, and that's it. That's as far as you can really go with that, okay? You really can't say anything else, all right? At this point, you go, well, now what do I do? Having done this with students a few times, this is the point at which students usually get confused. Never forget that once you get F net, even if it's an incomplete expression like that, the whole reason you got F net was to say that F net is equal to ma, which is Newton's second law, okay? So that's why we got F net. That's why we did all of this work to get F net, and we got F net so we could set F net equal to ma. Now, which m? It's actually m1 like that, okay? And so at this point, you could say, all right, fine, F net, we don't have a number for it, but we do have an expression. There it is. So do it like that, okay? So I can't put a number enough for F net, but at least I can go part of the way there and put Ft minus 32.5. That's got to equal. Do I have a number for M1? Yep, 13. Do I have a number for 8? Nope. And so that's it. That's as far as you can go, and we'll call that equation number 1. You can't solve it yet, but it's something, all right? And great. So now what? So now we'll turn our attention to M2, and M2 is the 6 kilogram, okay? There were two forces acting on it. There was M2G, like this. All right. So M2G is equal to 60 newtons. All right. And then there was also FT acting on it. Put a space in there. But guess what? We don't know how big FT is. All right. We didn't know over here, so, and it's the same FT, we don't know it over there. Didn't know FT here, we don't know FT there. Okay, and why did we do all this? Those are the only two forces. Why did we identify all the forces? So that we can get F net. And you say, all right, now what? What do you put in there? Let's go back to the diagram. All right. So if you take a look here in the diagram, we're looking at this situation over here with the 6 kilogram mass. It's accelerating down. Okay, it's being pulled down by gravity. And there are two forces. There's 60 newtons pulling down, and there's FT pulling up. Which one wins? Well, the 60 newtons down wins. Okay, has to win, because if it didn't, then, if the FT wins, then it would accelerate up. So the 60 newtons down beats the FT up. Okay, and so we can say that the net force must be the 60 newtons minus whatever the detention is, like that. Okay, so we don't have a number for F net, but that's okay. We didn't have a number up here either. The best we could do was, the best we could do for F net is get an expression. All right, so now why did we do this? We did this so that we could use Newton's second law. So this here, this line right here, you say, where did that come from? That's the second law. Okay, well, where did this line come from? Oops, hold on. Where did this line come from? Only with M2. It's also the second law. Okay, now the second law, but now applied to the 6 kilogram. And so this one's equal to 60 minus FT, and that's going to equal M2. And what's M2 equal to? 6 times A. And there we go. That's as far as we can go. Okay, if we had FT, we could solve for A, but we can't. Okay, and you say, well, now what do I do? Well, what you do is, the rest is really just math. What you do is you put these two equations together. You put this one here, all right, and you put this one underneath like this. Okay, and what you do is, it's very easy to solve. It's two equations and two unknowns. All you have to do is add the left-hand side to the left-hand side and the right-hand side to the right-hand side, and you get, the FT cancels out. So there's one plus, there's the other one, like that. Okay, and that's going to equal this one plus that one, like that. Okay, and you'll notice that FT here cancels FT there. So you're just going to have, well, I'll put it in another line. You're going to have that is equal to, and 13 plus 6, what's that equal to? 19. A. All right. And then 60 minus 32 is, here I've got the, is 27.5, like this. And that's going to equal 19A, and so A is going to equal, let me get the answer, it's going to equal 1.45 meters per second squared. All right, so that solves that one. Okay, so great. Did we answer the question? I asked what is the acceleration of the system, and we got that the acceleration was 1.45 meters per second squared. Okay, and does that make sense? Yeah, it has to be bigger than 0 if it's accelerating at all, and it has to be less than 9.8 or 10 meters per second squared. Okay, and 1.4 is less than 10. So yeah, it works. Now I'm going to ask you to do this one on your own. Okay, and I'll do it on Friday, but think about this one on your own, and because it brings up static friction. So I say repeat, but this time the system doesn't move at all. So in other words, this time the acceleration is 0. Okay, and just like before, like in this problem, see what we did is we had to do all this analysis and then we ended up with the acceleration. This time it's like you start with the acceleration and then you end up with the particular forces. Okay, so if the acceleration is 0, what happens? Well, let's go back to the diagram very quickly and I'll show you, or I'll give you a hint how this works out. Okay, so FT now is not unknown. FT, since this is 60, FT has to cancel that 60, so FT here is 60. All right, because 60 up and 60 down, they cancel, and that's what leads to no acceleration for the 6 kilogram mass here. Now, if this is 60, then this one must be 60. Okay, so that those two, because those two are equal to one another. And if this is 60, then guess what? The force of friction has to also be 60. Remember, this is kinetic friction, so now we're going to replace that with static friction. If this is 60, Ft is 60, then F static friction has to be 60, and you get that the force of friction is 60. And then you have all of the forces for this one. You're going to have 130 up, 130 down, 60 to the right, 60 to the left, and you've basically got all the forces there. And then finally, to solve for the coefficient, you make use of this formula here, just like we did above. You make use of that. Okay, so I'm going to let you do that. I kind of walked you through it, telling you what to do, but that's good enough for now. I will pick up from here, and also I didn't want to do this one because I kind of want to pick up from here for the third problem that I'm going to do next time. Okay, so let me take a look in the chat to see if there's any question. No one said anything. It always worries me a little bit when no one says anything in these things, because I don't know if you didn't hear me or not, but I did ask in the chat if everyone was okay. So I assume that you would have answered or said something in the chat if you didn't hear me. But if there are no questions, I'll just wait a few seconds. If there are no questions, we'll just end the stream, and we'll have another live stream on Friday. Hopefully, this has been helpful. Okay, and you'll be able to make use of this to at least get started on the assignment. Remember, if you don't finish the assignment, even if you navigate away from the page, when you come back, all of your stuff will be there. It'll just say, do you want to resume the quiz? And you can resume the quiz. I've tested it over many days, and it works. So of course, tell me if it doesn't. Okay, so no questions. We're going to end the stream. All right, bye-bye. End of stream.